We'll get into the certification of them. It covers 67 trace metals. So it's not all of them, but it's a big majority of them. And so kind of the premise of this presentation is not all filters are made alike. I'll kind of show you what I mean by that. So we'll go over an overview. We'll talk about filtration. We'll talk about the clean certification, what it really, really means, right? Because everybody has one, but they're all different. So section definitions. We're talking about sediment, right? Particles that are derived from sedimentary units, igneous rocks, whatever, breaking down and developing or creating metals in water systems, usually through weathering and erosion. Also, biomaterial can be considered sediment, but it's not really relative to this presentation because trace metals doesn't cover bio. Suspended metals, all right, are particulate from sediment. So we know what particulate is, sediment, retained by a 0.45 micron filter. Okay, retained. And then we have dissolved metals or trace metals that pass through a 0.45 micron filter. Right? And these are what we're identifying in analytical results to identify those trace metals, is those dissolved metals. And then we have total metals, right? We're all analyzing for what's the total metal concentration there and what's present there. So we can all agree to what those definitions mean. So overview, trace metals analysis is to identify and quantify dissolved metals that are present. 0.45 micron is very small, absorbs cellularly, so it creates biological issues in high concentrations of certain metals, right? Why are we filtering? It's regulatory compliance. It's required to do so under the Clean Water Act, starting back in 1972. And then analysis of suspended metals interfere with analytical procedures, which I mentioned earlier. And then health, obviously, certain metals can be really bad for us. We need to have metals in our systems, but not too much. Okay? So monitoring those water bodies to make sure that we're okay for drinking water, and other ecological systems will also help you. So metals, where do they come from? They're naturally occurring, and then they are also generated through man-made processes. Like, for example, construction sites are now becoming are required to do turbidity and metals analysis for erosion. Solid waste industry, we have these big piles of trash. As those metals break down, they precipitate down into the leachate, or if it's not aligned, into the soils. They have to be monitored and regulated pretty regularly. Obviously, metalworking, you're going to see high metal concentrations. There's many, many industries that are producing and creating metals. Especially here, mining. We're breaking down these structures and geology really rapidly. And so it's escalating the precipitation of metals into our waterways. So we've gotten really better at continuing and maintaining that, right? But there is still old mine tailings that are still wreaking havoc on some of our waterways, especially here in Colorado. So section definitions going into filtration. We're talking about micron or a micrometer, 1 millionth of a meter in size. Right? We're also talking about membranes or filter media. So basic operation of filter media is to retain certain items and allow certain items to pass through. So if we're looking at the relative size of a micron, pencil dot, if we were to take a sharp pencil and put it on a piece of paper, right? It's going to be approximately 40 microns in size. Your red blood cells are 7 micron. A yeast cell is 3 micron. So when I brew beer, craft brew at home, I use yeast, right, to ferment. And ultimately, I want to filter that out of my beer to create a nice, crisp beer. So I'll use a 2 micron filter to get those yeast cells out of my beer, plus any other particulate that is created from the grains and hops and everything else that I use in. So when we're talking 0.45 micron, we're talking really small. The actual paper of those filters look like they're solid, right? But it's actually made up of 50 to 90% open space, pores. So, talking about porosity, we have membrane sizes. So Geotech filters, we have everything from a 20 square centimeter filter. Do I have that size up there? So membrane micron size, I'm getting ahead of myself. So we're talking about empty space. We're using that sponge as kind of an idea of these open pores within this material. And the pore size is proportional to flow rate. So the larger our pore size, or our micron size, the greater our flow through that material. And a sponge is going to absorb stuff really quickly. As we squeeze it out, it's going to displace that moisture really quickly. But if we have tighter pores, then we're not going to have as much flow or transport of those fluids. And so Geotech micron sizes, they're going to range from 0.45 micron, which is typically used for trace metals analysis, to 1 micron, 2 micron, 5 micron, and 10 micron. So the higher the micron size is proportional to the flow rate. We get that question all the time though. What's the maximum flow rate I can get through your filter? Well, if you're doing trace metals analysis, I don't think flow rate's really all that important. Right? You're probably using it incorrectly, or you're using it for a different application that they're not really designed to be used for. Now, when we're looking at surface area, surface area increases the service life of the filter. So if we have a very small filter and we have a known amount of metals or turbidity that's in that water, a small filter is going to cake a lot quicker than a much bigger filter. So if you're utilizing filters and you're finding that you're using 1 or 2 filters per sample that you're collecting, maybe consider going with a larger membrane size. So membrane sizes start at 20 micron, 315, I'm sorry, not micron, squared centimeter, 20 squared centimeter filter area, 350, 450, 700, and 900. Right, those 900s are ideal for those applications where you have a lot of particulate and sediment in your sample. You may have to use them. They're a little bit more expensive, but they're less expensive than having to use 2 smaller filters. And so it becomes an economical advantage to that service life. Delta pressure as well. So the smaller the surface area, the less the delta. What is it? Greater the surface area, lower the delta pressure. So if we're running a very small filter, the influent pressure is going to be, the effluent pressure is going to be a lot greater change on a smaller filter than on a larger filter. But again, it doesn't really apply to our industry, but our filters are used in processes for filtering out materials in industry. And so their influent pressure, looking at the changes of pressure coming out of the effluent under the filter, does make an impact. And we have used our filters in some of those processes, even though they're not really designed. So let's talk a little bit more about the media types. So depth media is your primary membrane, which is an absolute membrane. So if it says that it's a 0.45 micron and it's an absolute membrane, it means that it's a true 0.45 micron. Those pores are actually 0.45. All right. If we go into a support membrane or a pre-filter, those are nominal sizes. So if it says that it's 0.45 and it's a supported membrane or a pre-filter, that means it's an average of 0.45 size. So you don't want to use a nominal filter media if you're really trying to get trace metals analysis. You want to absolutely have that absolute filter membrane certified. So if you put 99, it's about 99.9% of any particulate that's 0.45 micron or smaller will pass through that filter. Then you have serial layering. Serial layering is where you take your depth media, your pre-filter, because you have just a tremendous amount of sediment in your sample. So you have to pre-filter it before it goes through your 900 square centimeter filter. And so you can serial layer to also help take out some of that sediment load initially and then polish through your 0.45. A lot of our filters actually are built with a certain layer of depth media to kind of help take out some of that higher particulate load, especially with our versatile membranes. We should have some samples here so you can see that layering. Particulate retention, we have direct interception where an object of uniform shape impacts the pore size directly because it's just too large. It's not going to pass through. But we're also going to get bridging as well. We just happen to have two particles that are 0.45, for example. They just happen to impact that opening or pore size at the same time, creating a bridge. And then you have caking where your filter is just loaded, right? You put so much sediment onto your filter that fluids cannot pass through it efficiently. The porosity just isn't there any longer due to that caking, and so your filter is exhausted. We'll occasionally get customers that will call in and say, hey, your filters aren't working. Like, I can't get any water through your filter. Well, did you get water initially? Yeah, it was working great for like the first liter, but then it stopped. Well, your filter is clogged, it's plugged up. We'll have customers that will call and say, hey, like your filter blew up, it came apart, right? Well, what happened? Tell me a little bit more about what you were doing. Well, we were flowing through the filter, water was flowing great, it stopped. So we cranked up our electric submersible pump to increase our flow rate, just over pressurized the filter and just separated the two bonded pieces. So caking does happen with filters. As long as you understand kind of the principles of how that works, you can avoid getting groundwater all over your site or all over yourself, or trying to troubleshoot a filter that's just simply caked. So here's kind of a list of Geotech filters. We probably have, from my competitive analysis currently, they're the broadest number and types of filters that are available in this industry right now. We're running with a VersaPore membrane, which was our original filter membrane that was developed for the EPA and the U.S. Geological Survey. The VersaPore material was specified by them. The pore size is an absolute pore size, and its clean certification is one of the greatest in the industry. So we really created a high bar for us to reach. We thought it was impossible at one point, but we got there, and we've been able to maintain it, which has been great. And I don't think anybody else is meeting the same certification. But then we have a variety of different sizes. So all of our VersaPore membranes, the 0.45, the 1 micron, the 5 micron, and the 10 micron are all absolute pore sizes. So it is a true micron size. So if you're doing eDNA or you're doing other types of filtration where you need a larger pore size for whatever reason, then you know that you're actually getting the true passage of particulate or biomatter larger than that. And then we have a polyether sulfone. So then the 0.45 also comes in different sizes, membranes, again, service life, right? So if you have really, really, really clean water, go with the 20 centimeter. It's really affordable. But if you're doing groundwater, you're going to definitely look at that 350. And if you're caking that, jump up to that 700, all right? Polyether sulfone, PES membranes. So we brought these online because all of a sudden all these competitors started emerging, making filters that were lower cost than our VersaPore filters. And we started to see our numbers drop. We're like, what the heck is going on? How are they selling these filters for so low? So we did a little investigation. We learned that the polyether sulfone is a lot lower cost of materials, and that the certification on it is also lower. So we can reduce our costs altogether, right? So we came out with our own PES membrane, which is a great membrane. It's still an absolute pore size. And then we increased our size on our top end of our filter area to 900 square centimeters. So that's where we have the big range of sizes or filter media sizes with two different types of membrane types, right? And it includes the supported membrane on the inside of it as well. Supported membrane as well as the depth media, so it's got a little bit of pre-filter in it. And then we have our polypropylene membranes, which do have high particulate loading capabilities, just based on the size, but they're only available kind of in that pre-filter size, 1 micron, 5 micron, and 10 micron, and it's a nominal membrane. So it's just designed to be a pre-filter, in case you're caking your 900s. And you may want to put that polypropylene in there. They're really inexpensive, there's no certification for them. It's kind of an average pore size, so it's going to just take some of that heavier load initially. Just basic anatomy of our filter and most people's filters. You have the influent filter end. Some companies mark the direction of flow. It's really important that you actually use that directional flow for the filter to work properly. Polypropylene capsule body. We're also coloring and labeling all of our filters that are very similar. So our VersaPore membranes, for example, on our 900s are red, and then our polyether sulfone, I'm going to call it high capacity, is also red. So we kind of tell that those are the higher or larger membrane sizes.
What color is the third one?
I think it's green.
Okay. That's the pre-filter. Just green.
No, the pre-filter has no color.
Oh, okay.
Yeah. No, we wouldn't make our own. It's just on the 0.45s. So the industry talks about, through competitive analysis, ultra-high flow or ultra-high capacity. But their actual membrane size is 600 square centimeters. All right? So if you get caught up in those terms of high capacity or ultra-high capacity or extreme capacity, it doesn't mean anything. All right? Look at that membrane size. It's a 600 square centimeters. It's 900, it's 900. Right? We could call our 900, which I think is one of the biggest membranes in the industry for trace metals analysis, like infinity, extreme high capacity, right? But we're not going to use that marketing jargon. We just want to educate the industry that, hey, larger the membrane, more service life you're going to get out of it. So be careful with that. Flow direction indicator. We also have a tube adapter, so filters are really clunky, right? They have this weird threaded piece. We're always connecting tubing to it, and only one size of tubing really works, and it's really hard to get on anyway. So we made this little machine, this adapter that threads on, and it's a stepped bar. So then you can put on a 0.170 inch inside diameter tubing, or 1/4 inch, or 3/8, or even up to a 1/2 inch. So it's really universal based on the type of tube that you're using. And you only need one per filter because it's only coming in through the influent, right? Because your effluent is just going to go directly into your sample container. Yeah. Internal capsule characteristics. Again, absolute rated pore size membrane on all our 0.45 micron filters. Very important. Not everybody's doing that. So please, to get your data, representative data, make sure you're using an absolute rated pore size, whether it's ours or somebody else's. We also metal tested and lot certified. And then we have a high throughput membrane. Doesn't really matter if you're really looking at high volumes, probably using it for a long application. So let's talk about analysis. So our filters are manufactured in a factory, right, with people, and you're analyzing for trace metals, maybe. And if you are, you want to make sure that your filter is not contributing metals to your sample. And so we take lots, every single one of our lots, we'll pull random samples out, we'll go through a lab analysis for 67 trace metals, and we are going to guarantee that our filters are not going to contribute to more than 0.8 milligrams per liter of aluminum to your filter. Chances are we're non-detect all the time, but that's our threshold that we've hit with the USGS's requirements and EPA's requirements. So if we exceed any of those numbers on any of those 67 trace metals, we scrap a lot. Right? It's unfortunate, but we can't get those out in the market because we have a certain standard to uphold. I'm not going to name any names, but some of our competitors, their low limit or detection limit is 10 on aluminum, which is high. In some parts of the country, if you hit 10, you're going into remedial action, right? And so if your filters are contributing that much aluminum potentially to your sample, because that's their detection limit, run those equipment blanks. Make sure you know where that source aluminum came from, and you're not potentially telling your client that, hey, all of a sudden we have a spike of aluminum at your site, and you need to investigate this more. And it turns out it just came from your filter. So these are very low levels compared to industry standards. So as long as you know how to read that, everybody has a certificate, but their numbers, I almost guarantee, are not as impressive as this. Our polyether cell phone filters, just as a disclaimer, have 50 trace metals, and their limits aren't as low as these either. So this is based on the VersaPore membrane. Cool.
Yep, you're up.
Okay.
On here.
Hello, welcome to Exploration of Metals and Methods with XRF. Just want to thank Andrew for the metals beginning there. Everybody tries to grab those Dispos-a-Filters and shoot them with an XRF. And I always say, well, you're getting a lot lower detection limits with the filter itself. I'm not sure why people want to buy them and then shoot them with an XRF. It's kind of funny. I just want to briefly, in case you missed anything else that's in the house, I'm dealing primarily with XRF, total elemental analyzers, and lead paint analyzers. But we've also got the Leptron, these are all manufactured instruments by Geotech, in case you missed any of them up here. And then we've got the ones we represent, our Bruker and GasMet, as well as Ray Systems, Honeywell now. So we have these various amounts, as well as the Dispos-a-Filter just talked about. Just want to make sure you didn't miss anything out there. So we rent, sell, clean, calibrate, train people how to use, and repair. Just want to make sure you know where we're coming. I'm going to focus on XRF, and we're going to get started with the technology and where it came from. In 1895, Röntgen kind of discovered X-rays on accident. He had left some bitumen paper out and it hit sunlight, and suddenly discovery of X-rays were happening. This was simultaneously happening all around the world, because within 2 weeks they were generating X-rays at Dartmouth College for diagnostic medicine. So it's kind of amazing. Without the internet, when a discovery is made, there's people using it within seconds. I'm not quite sure how news traveled so fast, but in Germany, 1895, within 2 weeks, they had X-rays in other parts of the world. So with X-rays, along came Moseley, who discovered the relationship between wavelengths and atomic numbers and allowed spectroscopy to be used in X-ray fluorescence. So he's kind of took the idea of X-rays and put it into a practical application for being able to analyze heavy metals and materials and just any type of elemental analysis we can thank Moseley for. So we had these gigantic X-ray instruments to begin with. The size here, you see this gigantic machine here. And we can thank Marie Curie for the portability of them. She was actually working on her radium in 1913, stirring. And we can thank her for polonium and radium, as well as radioactivity and its uses. But what she did was the war came, and she was in France at the time, and she was kind of in danger. So her life's work of stirring this radium, she had to kind of put on hold. So she put it in a container and lined it with lead and put it on a train to Bordeaux and deposited it in the bank, in a safety deposit box at the bank, and then came back and decided she was going to put her scientific mind to helping the war efforts. And what she came up with was the portable X-ray cars. So these, she's got an X-ray. See, she figured that to help the doctors identify injuries in war, she would be able to, so they would take these cars and drive them to people that were injured and shoot X-rays of them and identify where bullet wounds were, where the bullet was actually in the body, as well as whether they had broken bones or whatnot. So it's kind of amazing. She asked the French military for funds for this, and they kind of didn't pay any attention to her. So she had a pretty good reputation in France because she had won the Nobel Peace Prize in physics in 1903. So she went to all the women in France and the philanthropists and asked for money. And she came up with enough money to make 20 of these cars. And it really kind of pushed their war efforts and allowed them to get their injured people taken care of very quickly. Just to move on to X-ray fluorescence and how it works. So we all probably recognize the Bohr model of an atom here. You've got your protons and neutrons in the center, and in the outside, you have these electrons that are arranged in these shells. So that's what we're doing with XRF is we are taking either an X-ray tube or a radioactive source, and we're emitting X-rays and gamma rays into the sample. And we're ejecting an electron. And that's causing ionizing radiation. We've got an atom that's unstable and it wants to become stable. So these outer shell electrons jump down to fill these vacancies, making the atom stable again. But in order to do so, it needs to give off energy to do that. And this energy is in characteristic energy. So we can see whether it's iron, molybdenum, nickel, chromium, lead, whatever these characteristic X-rays are, we catch them with the detector and can quantify them and give you concentrations in parts per million, milligrams per square centimeter, micrograms per cubic meter, whatever the instrument is calibrated for. We take these X-rays and quantify them and display on the screen for you. So in the nutshell, we've got our source, whether it be an X-ray tube or a radioactive source, emitting X-rays and gamma rays into the sample. And characteristic X-rays come back to the detector. It gets shoved through a calibration. The raw data is typically saved, and the data comes up as either L shells or K shells. And these are the actual X-rays coming back to the detector that you see on the and there's very little difference. The signature looks the exact same for each one. And we either use the K shells to identify parts per million or L shells, depending on the sample and what's fluorescing better. And then it gives it in the milligrams per square centimeter or ppm or micrograms per cubic meter, depending on what your calibration is. So once again, depending on whether it's whatever is out of each sample, what looks better, you can calibrate it on. If you're trying to calibrate an instrument for various elements and you have some a little bit of coelution where you've got your peaks kind of mixed together, you can choose to calibrate it off the K alpha, either the K lines or the L lines. And so it's most soils samples are K lines until you start to get to things like gold, lead, and tungsten. So with X-ray fluorescence, we can actually see, we can excite all the way down to fluorine, actually detect some fluorine with the Bruker tube XRF, which also allows you to analyze sodium. So sodium all the way through uranium is about what our practical elemental analysis is with handheld XRF. Again, this is just handheld XRF. There are further capabilities with the benchtop units. So a basic rule of thumb for measurement times with these handheld XRFs would be if your sample, your elements are 10% or greater, you can get your analysis in about 10 seconds. So if we're talking about a metal sample that's an alloy, and you're talking about 10% of this and 40% of copper and 20% aluminum, you can get your answer in pretty quick time. Like a 10-second analysis will allow you to separate even some of the hardest alloys to separate. But for if you're down in lower numbers, all the way down to limit of detection, you want to take analysis that's at least 60 seconds long. So your measurement times are going to be dependent on what your sample type is. So for alloys and elements that have great percentages in the sample, you're going to be able to do a shorter sample time. as opposed to if you're trying to do exploration in mining, you're going to want to take longer readings down here in the 60 to 120 second. The greatest thing about XRF is that it's statistics. So the longer you analyze, the more precise your reading is going to be. Each fourfold increase in time equates to the doubling of the precision. So longer, the better, up until diminishing returns. If you get your answer in 10 seconds, and that's sufficient for high concentrations, there's no sense in taking a longer analysis, but we'll show that. So there's two basic ways to generate X-rays. We've got an X-ray tube, which in the time of Ronkin and Moseley, the X-ray tubes were gigantic, the size of your arm or whatnot. And with the industrialization and miniaturization, we're able to get an X-ray tube smaller than a coin, or about the size of a coin. The other source for exciting X-rays is an actual radioactive source, and they're always in these sealed capsules, so they're completely contained in stainless steel. This is an americium-241. It's completely contained. It's kind of one of the more exciting sources, one would say, because it has a half-life of like 432 years. So it's pretty important not to lose that anywhere. They often weld these into the XRF so that they don't fall out at all. And lose them. A little bit how the XRFs work. A tube XRF, when you pull the battery, there's no X-rays being generated. So there's a little bit a difference with compliance when you're using it in different states, and compliance as compared to analyzing with a source, an X-ray device with a source in it. So with the tube, you've just got a filament, a high voltage is applied to the filament, and these electrons travel across here and hit a target, and that's how the X-rays are actually created. So once you pull that battery, you can't create these X-rays. And they use different anodes depending on what you want to analyze. If you don't want to, there's a rhodium tube that's kind of out of the way of most of the precious metals folks look for, or a silver tube, so silver anode. Depends on what you want to excite, which elements you're looking for. So the devices, XRF devices, they're either handheld or desktop or actual benchtop types. The XRFs that we carry are the Viking detection, which uses a cobalt-57 source, so that's a radioactive source. The Bruker S1 Titan, which uses an X-ray tube. And the tracer also uses an X-ray tube, as well as the Bruker CTX, which is the benchtop. What's nice about it is you've got this chamber that's completely lined, so you don't end up with any stray X-rays happening out of here, as opposed to like right here. This is probably a bad example because it's got a rock on top here, and there's no safety shield. There's no top to stop any of the X-rays that penetrate the rock. So with handheld XRF and benchtop, desktop that you see here, there are endless applications. You can do positive materials identification. So you can identify the difference between 60-65 aluminum and 70-72, as well as like in all of the petroleum industry. After that gigantic fire at an Exxon plant in Texas, they came up with it was because one of the weldings that were done and the change of material was not up to grade. So they mandated 590A, which mandates that every in-process piping in any utilities, refinery, or any type of plant that pushes material through processes like this has to have 100% PMI, positive materials identification, which means you identify what materials are in place so that they won't degrade and you won't end up with an explosion like that. Because when you're pushing all these chemicals through a pipe, you can end up with an explosion if it degrades the material and catches fire, and lives can be lost. So some of the other applications, like the aerospace industry, they also mandate 100% positive material identification. You can, I don't know, there was a flight coming from Puerto Vallarta where the pilot lost control of the plane. It was one of those fasteners that hold the rudder back together. It snapped. The material was supposed to be 70-25 and it was 70-50. And there's just a little bit of zinc and manganese difference, but that little bit of zinc and manganese difference caused the fastener to degrade. And when it broke, the pilot lost control of the airplane, went up and down and plummeted into the ocean. So in the aerospace industry, you have to get 100% PMI if anybody's selling any types of fasteners or any materials to anybody in aerospace. The point here is that with XRF, you can analyze any materials you want, depending on what your elements of interest are. It's useful for identifying in practically anything. You've got jewelry, you can identify purity. So if someone's got a pawn shop, they want to identify what kind of material someone's bringing in, they throw it on the XRF and come up with, you can identify whether it's 18 karat or 14 karat. It'll give you, it'll read out in carat as well as percentages for precious metals as well. It's highly used in the mining industry, as well as the environmental cleanup, which I'm going to go into further. I just kind of wanted to touch on this, but obviously it's a sinkhole here because there's just so many applications, and it's for toys, you can identify for Consumer Product Safety Commission, which requires that, we don't poison our children with lead and cadmium. It's just, there's just so many applications, and it's easy to just fall into that, but I'm supposed to be focusing on mining and environmental. So I'm going to move ahead here. So I just want to point out with these applications, you always want to put the instrument directly on the sample. Air causes error. You want to be as flush to the sample as possible so that all those x-rays that you're exciting and coming back to the detector can read those characteristic x-rays. You want to make sure they come back to the instrument. This is kind of a cool application. It was at the Hearst Castle. It's a sarcophagus, and they wanted to find out if there was why there was pigments of copper on it. And it turned out at one point it was completely covered in copper. Kind of exciting stuff. So when we're analyzing for elements in soil or for mining purposes like exploration, there's 3 different approaches that you can take, and it really depends on your data quality objectives. For a fast screening, you can go directly on here. Now, this girl here is shooting directly on a rock, and she can determine for mining exploration purposes if there's any anomalies. The whole idea is to take lots of measurements and identify trends. You're looking for any anomalous trends to see if the property is worthwhile. So instead of dragging a talus or heavy samples back to the lab to analyze, you can get an idea of what's happening with the geology of an area very quickly with this fast screening tool. Same for environmental analysis. If you've got some contamination you're concerned about, you can completely delineate a plume of contamination just by analyzing meter after meter. If you want, and that's a fast screening tool to give you a quick idea qualitatively what's happening. If you want better results, you can actually bag a sample for environmental cleanup, take the sticks out and the rocks out, maybe send it through a 60 mesh sieve, and identify. It gives you a little bit better analysis because the particulate size is more homogeneous. The more homogeneous you have, the more homogeneity, the more accurate your analysis is going to be. And you actually get pretty decent lab correlation with a quasi-homogeneous sample. And for your best corroboration with a lab, you would grind it and sieve it and send it all the way through several different meshes till you get like a very small particulate size, and pack it into an XRF cup and shoot the sample in a controlled situation like this, and you can actually get an R squared valued with a lab of a 0.98, which is extremely good data. So here's an example of finding the contamination. Instead of like, what if you were to just choose lab samples? You have a limited amount of samples you're going to run because it costs a lot of money to send samples to the lab, and plus the wait time on it can be 2 weeks, 3 weeks. So with the XRF, you have the ability to shoot every meter, every 10 meters. You can choose and kind of until you suss out where the plume of contamination is. And for fast screening, this is actually compliant with US method EPA 6200, but that allows you to find it without, like, if this is kind of miraculous that they missed the entire plume, but you could actually, it could take you several times going back to get samples and sending them to the lab to find the plume of contamination, as opposed to just using in situ XRF very quickly. So that's how you're going to determine what approach you take. What are your data quality objectives? Are you just trying to identify the plume? Do you want to find out whether or not you've cleaned up enough? Are you going to use it while you've got a backhoe mobilized on the site? A lot of people, they'll shoot samples, scrape off a couple of or 6 inches or so, and then shoot some more on directly in situ, and allows you to on site move contamination off your site. So in situ is direct analysis. There's zero preparation, and it's an excellent fast screening tool. So this type of result can actually get 0.83 R squared value with a lab. So that's not a bad correlation considering it's quick and dirty. So when you do get your bagged samples, your correlation is better with a lab, with a bagged sample, because you're able to take out the sticks and rocks. And then if you do a fully prepared sample where you've ground it and sieve it and got a nice homogeneous sample, your R squared value is 0.98. So you can get really good results depending on what your data quality objectives are. Now, should you go out there, if you're trying to just figure out the plume of contamination, should you be out there preparing samples? Likely not. It's best to just use your fastest screening tool. So you determining your data quality objectives is going to help you determine what your approach is. Some of the considerations are the natural heterogeneity of a sample, the particulate size, moisture will affect your readings. You want to make sure that you have less than 20% moisture. If you take a handful of soil and squeeze it in your hand and let go of it, if it retains the shape of your hand, you have about 20% moisture in your sample. And that's okay to shoot with XRF. You don't have to do any drying at that point, but any wetter than that, and you're going to have to either dry it by leaving it in the sun, or if you're not worried about mercury, you can actually put them in a little oven to dry them in. So yeah, here's moisture. You want to make sure you're not shooting it directly into water or moisture. I've had folks shoot moisture samples. You can, if you shoot them while they're moist, send them to the lab and get the data from them, and then you can kind of produce a fudge factor and identify, okay, we're going to just shoot it wet, knowing that it's this far off. Kind of gets a little wild out there once you start changing your objectives or accepting data that's been kind of manipulated. So about 20% of your, you can figure if you've got 20% moisture, you're about 80% true of your sample. So interpreting your results, one of the greatest advantages of XRF is that you've got your parts, your element, your parts per million, and an error value. Not many instruments have this. So what you see is you can actually calculate, have I taken a long enough sample? If you look here at number 14, it was like a 0.3 duration. That's an accident. So you know right away there's nothing to look at here. But your duration for your 13, number 13 here, you've got 138 parts per million. And the instrument is telling you it's plus or minus 16 basically. And that's off of a 30-second analysis. That's some pretty tight data. You don't need to go on from there. If you had, if you're, yeah, I'm gonna move on to some hands-on here. But the point with this is it's going to dictate how long you analyze. If your error is half the value of your reading, then you're going to want to take a longer analysis. You don't want to trust, like one of the problems with the folks out there in mining is if they've like, look at all this gold I've found. I've got 100 ppm gold, and then you look and the error is at 50 ppm. That's not really that's not valuable. So you're going to want to take a longer analysis. So you can determine your time of how long you analyze based on your data quality objectives as well. So if you're out in the field just doing some general cleanup and you're in your plume contamination phase looking for concentrations, if you've got 500 ppm lead and your action level is 100, and you're in 10 seconds, it tells you you've got 500 ppm lead plus or minus 100. You can stop your reading in 10 seconds. It's kind of a nice tool to be able to have to see your error. I think I've got some, the instrument here. Let me change the, from my share content. Did that stop?
You can just see,
What's that?
now we see your go-to XRF.
Okay, thank you for telling me. Yeah, I want actually. Oh, you mean you haven't seen Go to XRF? I mean, you haven't been seeing the
Oh, we saw the whole.
CV.
Now we
Okay,
see.
thank you. Excellent. So I wanted to go here and show you the instrument. I have to apply a background that does not have any type of thing so that you can see it. So here we have the XRF. So this is a handheld XRF. And I think it's about time to move on to safety. Is that right? Or
Keep going if you like. You're fine.
should we just move on with it? Or all right.
Just a quick hand run. You're fine.
So am I going to shoot the sample like this since we're moving on to safety? Do you think this is a good idea to shoot it like this?
No.
Well, you guys get 100%. I think all these people should be certified, Andrew. Oops. Here, I'm going to pull this aside and drop this instrument right in here. So what's nice is you also have the ability to put this instrument in its little
Evelyn, you want to check the question in the chat box?
I didn't see one. I just asked people if they had any online.
Oh, okay.
I don't see anything in the chat box there. So this is what a handheld XRF looks like, and here's what I meant about being able to put it in a test stand so that you're for safety purposes, as well as sometimes a little better analysis. But the beauty of the handheld is being able to shoot it directly in situ. And we went through data quality objectives. Are there any questions about preparing samples versus not preparing samples, or? No,
Um,
no question. Oh, we have one?
I did have one question for you, Devlin. How deep can an XRF penetrate? Like how deep can you detect?
Excellent question. That depends on the density of the sample. So when we're analyzing for PMI applications, analyzing alloys, it's only going a few microns. You know, you've got a metal sample, you put it on the instrument, it's only going to give you penetrate a few microns. With soils, you're going to penetrate through definitely through like an inch or two, depending on the density of the soil. But what's important is what's coming back to the detector. Like you might be able to excite things down an inch or two, but those aren't going to come back. So usefully, you're able to penetrate about 3/4 of an inch for a soil sample based on the density of it. As well as like if you're dealing with plastics for a consumer safety or consumer product safety commission type of application, your plastics tend to be not very dense at all. So there's a lot more backscatter and you're penetrating through most of the plastic with that. Is that sufficient?
Yes, thank you.
Okay, excellent. Yes, so I'm gonna move on to safety. Is this, Andrew, do you need to have any kind of change over here at all for moving on to safety?
Just go ahead and transition in.
I'm sorry, what was that?
Oh, go ahead and just transition in. That's fine.
Oh, good. All right, I'll go back to sharing PowerPoint and then we'll move on to shooting some samples with the XRF share content. Okay. Sorry, I had 2 PowerPoints up, so I need to make the transition here. If you'll excuse me. I think I've got you looking at the wrong one. Does that look right?
It does, yeah.
Excellent. Okay, so there is an XRF safety certification course on our website. I'm going to kind of go through some of the safety features of using an XRF. And once you take this quiz, you'll get a certification for using the XRF and being able to rent the unit. It's just something that allows us to be in compliance with the various states that we rent in. And it shows the regulators that we're conscious of who we're renting our instruments to. So we mandate that people take this XRF safety quiz and have a certificate in order to rent. So I'll put the link at the end of it here, but we're just going to go through a little bit of it, talking about definitions of radiation exposure, practicing ALARA, a little bit about XRF basics and instrument safety. So when we're talking about radiation, we're talking about any type of X-rays or waves. There's short wave, anywhere from like a shortwave radio all the way up to high intensity gamma rays from the sun or what have you. But for our purposes here, we're talking about generated by an XRF. So radiation is actually the emission of energy or waves from high energy particles that cause ionization. And the process of ionization is when you actually eject that electron from the sample. So an X-ray, again, is it's what we're considering that's coming back from the sample. X-ray fluorescence is the characteristic X-rays that come back to the detector. I'm sorry, I skipped over here. X-ray is the energy wavelength that we're sending into the sample here, electromagnetic waves of high energy, whether it's gamma rays from the nucleus of a sealed source or from the electrons. So some of the things we're concerned about with radiation is what our dose is, and we're allowed a certain number of dose, which I'll get into later. But we're talking about the effects on tissue once it's deposited into a tissue, once we've been exposed to ionizing radiation. So we talk about it in terms of a radiation absorbed dose, defined as a RAD. And we mostly look at REM to measure exposure, because that takes into account the type of tissue that we're looking at, as well as the type of material that it's coming from. So for our purposes, when you send in measuring radiation device like a dosimeter, they read out in REM, because it tells you what the effects are on your body. So depending on what type of rays we have here, alpha, X-rays, beta, gamma rays, you have different, they're going to penetrate at different levels. You've got alpha particles that are stopped by paper. Beta can be stopped by your skin. Gamma rays can penetrate it through lead to a degree. You need a certain amount of lead. So most of the XRFs are actually shielded by lead. And then there's neutron particles, or those nuclear density gauges. Those are the only instruments that we use or probably encounter in our field here that have this high of a penetrating X-ray. So I can turn on a Geiger counter and I could find a Truxler gauge 40 feet away. That's how high the radiation is from those.
Types of radiation are produced from XRF, good one.
Pardon me?
What type of radiation is generated by an XRF?
What type of radiation?
Based on the previous, we're looking at alpha, beta,
Gamma rays, like gamma rays and X-rays are what are being produced by the instrument. So with a sealed source instrument, you're dealing with gamma rays because the nucleus of it is emitting gamma rays and X-rays from the outer shells. And then an X-ray tube generates X-rays into the sample. Are those questions, or I hear like kind of background?
Some loud people in the hallway, we're trying to keep the door
Okay,
shut.
thank you. I lost my image of you guys and I'll lose my whole window here, so I'm just gonna live without it. So we get a lot of radiation just from naturally occurring radiation, as well as diagnostic medicine and whatnot. So for and also living there in Denver, you guys are getting a whole lot more cosmic radiation than I am, because you're closer to the sun than I am here at sea level. So there's a lot of kind of expected sources of radiation that we get. And there's even been a lot of studies on how low levels of radiation are probably good for you. It's kind of interesting. We try to stay away from radiation our whole lives, and then we discovered that low level radiation is probably pretty good for you. But here's some of the, like when you take an airline trip, you're actually being exposed to radiation. A round trip is about 5 millirem per year that you get. There's also like a nuclear power plant, coal burning power plant that you get some radiation from per year, 2 millirem. We also use in occupations, we've got nuclear power plant workers or X-ray techs, medical personnel who get exposed to radiation. You also get exposed to radiation just going in to get your teeth X-rayed, or your body parts X-rayed, or a CT scan, or an MRI. So there's an expected amount of radiation that we get just from living with natural sources, and then man-made diagnostic medicine type sources, as well as using an instrument that produces radiation. So when we start using an instrument, we try to practice and keep our exposure as low as we can. So using an XRF, the maximum permissible dosage are about what is 6 5 REMs in a year. And using these instruments practicing ALARA, you're probably going to get 0.2 millirem per year. That's using an instrument 5 hours, 5 days a week, 8 hours a day. Type of situation. So in order to identify how much we've been exposed to, we can wear a dosimeter. And a dosimeter, you wear it for either quarterly or monthly, and you send it into a lab, and the lab sends you back tells you what you were exposed to, as well as a new dosimeter. I used to have an issue. I went through the X-ray at the airport, and I had to explain. I would write down to them every time, oh, I went through the airport X-ray twice or 3 times this last month. And they would always, they finally said, why don't you just take your control badge with you? Because these are issued with a control badge. So if you take that control badge and put it in when you go through the X-ray as well, then it'll have a baseline that's accurate. You don't have to write a letter to them. So, it helps you kind of keep an idea of what your exposure and to ensure that you're practicing ALARA when you get your data back from a lab that says what your level of exposure is. I think we covered, in case anybody's new, I wanted to talk about the basics of the tube X-ray and how you're being exposed basically to X-rays that are being emitted from the XRF with an X-ray tube. And that's the technology of heating up a filament, and these electrons flow to a target, and the target produces X-rays. So one consideration for regulatory folks is that it is an open beam. So that means you pull the trigger and anyone in front of the shutter can get exposed to it. But by the same token, you can also just pull the battery and not produce X-rays, as opposed to a sourced instrument that a sealed source, it's constantly giving off X-rays. It's constantly decaying, giving off gamma rays and X-rays. So that's why a lot of states require dosimetry to be worn with an XRF that's got a sealed source in it, or they also require, some states require licensing that are different, that are a little bit different. Any questions about the 2 types of radiation we're emitting out of XRFs? Okay, we'll move on to safety. Let me see how much time. Okay, so safety-wise, when operating XRF, the mantra is ALARA, and that's to keep your exposure as low as reasonably achievable. So the 3 basic principles of protection against radiation is time, distance, and shielding. The amount of time you're exposed to the shutter while the shutter is open is what they're talking about. You want to make sure that if you've got an instrument that has a very old source in it and it takes longer to take a reading, once you're hitting like a 5-minute sample, then you're kind of just spraying X-rays into the air and exposing people, and your data is taking really long to get. So it's important to kind of resource your instrument from an ALARA standpoint, trying to keep your exposure as low as reasonably achievable, as well as your distance from the instrument. If you're in the field analyzing directly on the ground, you don't want to have your feet right next to it, or you don't want to have your hand next to it. If you're shooting on a wall, if your hand is right next to it, you're not your trigger hand, your other hand is anywhere near the snout of the instrument, you're needlessly exposing yourself. You don't have to stand back from the instrument from a distance, but just don't have your face down in there trying to make sure that the shutter is open. As well as shielding is the 3rd principle of radiation safety. They're mostly shielded with tungsten, as well as the test stands have like a tungsten lining on them to make sure that you're not being exposed to the X-rays. So some of the dosimeters that you can use to identify your exposure. There you got dosimeter rings or the ones that clip on to your collar. Important thing is that if you are using dosimetry, is to wear it while you're operating the instrument and not while you're going to the dentist. Just using it while you're during operation. So operating an XRF safely, if your application will allow it, certainly put it in a test stand where it has this nice covering and it's being you're being shielded from any x-rays. But if you're a single person out in the field shooting into the soil, you just want to make sure your feet aren't right next to it, right next to the snout. You don't want to hold it with your legs and press, pull the trigger. Just have your legs, your arms and legs out of the way of the beam and practice ALARA, even when you're in the field by yourself. So that's before actually using the instrument. Make sure that you're aware of your surroundings, aware of if anybody on site. If you're pregnant, your dosimetry, your exposure rates drop per gestation period. So you want to make sure that you write in the eyes of the NRC, if you don't notify your RSO in writing that you're pregnant, then you're not considered pregnant. So that's something to do, and then reduce your exposure to 9 months. So it's your responsibility when you rent an XRF. It's important to know when the primary beam is open. You don't point it out yourself. You don't point it at anybody else. You just act responsibly, as well as know what you're shooting. When you're shooting samples with low density, you're going to have a little more backscatter. So that's backscatter from here. So you don't want to have your hands over here shooting directly into the sample. There's no reason for you to have any body parts in the way of the backscatter. So if you have a piece of material that's an alloy, it absorbs a lot more. And early on in the 90s, folks were selling XRFs and people were actually holding samples in their hands and shooting it. And they're like, oh, it's metal, it absorbs all of it. And that's not quite true. They kind of really had to backpedal there and start training people that no, you shouldn't be holding any samples in your hand, especially when it's just as easy just to wedge it against something or just keep it low, keep it on the ground or on a stand or table of some sort so that you're not exposing yourself. Are there any questions about safety, operating an XRF safely? Okay, here's where you can take this quiz and you can take the XRF quiz here and then you'll get your certification. And I'm going to go over, let me switch over here to shoot the analyzer and kind of do a few reshare this. Okay, so you've got the XRF here. Let's kind of show with let's look at some of the radiation exposure that we're not getting. See, with this, I've got a Geiger counter here. And there's a little bit background coming out. See, the instrument will automatically shut off if you don't have a there's not a sample in front of it to absorb some of the x-rays. I'm going to switch over and just do a few analyses with the instrument. Any questions?
Nothing on chat right now.
Okay, thanks. Is it just you? Jason? Let me see, where's my, okay, so I believe you can see the instrument here, the test screen. Okay, so I'm gonna go into an analysis here and hold the trigger.
And what sample did you put on there?
I've put on a soil sample here, so I'm just illustrating. Here's the safest way to take a measurement is to put it in the test stand. Before you begin your analysis, you want to shoot your standard. I've got a TIL 2 standard, and I know that it has 31 ppm lead in it. So I'm going to take a 60-second analysis and have a look to see what it is. And this is what I was talking about, where you've got your element, your parts per million, and then your 2 standard deviation. So operating as safely as possible in the test stand, I'm shooting my standard. It's going to switch over to the other. I've got 2 phases, 2 different filters that the instrument's running on. And that's optimized for different elements, each filter is. And the lead is actually on the second filter. I've got it in a, what's important when you're shooting is to have it in the appropriate calibration. You don't want to shoot mining samples in a lead paint mold. It's gonna not provide much information and it'll give you lousy answers. So here's a 23 plus or minus 12 here, and this is only 30 seconds on that second sample. So we've got, it's still within the range of 31, but just the whole idea, the longer you analyze for, I can change my time and analyze for a longer period of time just to get my precision down. So that's kind of the advantage of XRF, is being able to decide based on your data quality objectives, what your analysis time is going to be, what you're going to be shooting, how you're going to set up your analysis, whether you're preparing your samples or simply analyzing in situ. It really depends on what your data quality objectives are. Does anybody have any projects, or is there any questions about anything?
Has anyone developed a downhole application for this? Like a geoprobe map?
You know, I haven't stayed up on how far they are with it, but where's my? Sorry. But I know that the Navy had some downhole analysis where they had their own, they had it on a probe and they were able to drill down and then kind of send the XRF part of it down there, the detector part. They would kind of be shielded at first and then it would slip out and they would analyze it. So that's as close as they've come to being able to do downhole. But most of the way the mining industry uses, they analyze the core that's coming out of the the core that's coming out of the ground, and they can actually identify whether they want to analyze if they want to continue drilling in a hole. They can actually call a hole based on their data that they're getting from core that they're analyzing, either with a geologist figuring out where on the core to shoot, or a scanning technique. Here we go. Any other questions?
Still nothing on the chat.
Look in the chat.
I might have missed it, but what does LOD stand for?
Limit of detection. And that's what your limit of detection is for that element in that particular sample. And what's nice is most XRFs, they show you what's detectable. They give you your elements that are detected with your error, and then they show you what elements are below limit of detection, as well as below that, they show you what that element that's below detection, what it would have to be in that particular sample in order to be detected. So it's kind of, it's just such a great technology to be able to do that. And it's based on the sample that it's looking at and all the returning x-rays and the scatter. There's really a lot of computation going on with XRF and each sample and the amount of information that you can derive from one sample. So that stands for limit of detection. And we get that question a lot. Oh, what's the limit of detection for arsenic? And you were down to about 2 to 3 ppm with handheld XRF, which is quite astonishing. And that's with a fully prepared sample. But the question is always, well, can you lower the limit of detection? No, we can't actually lower the limit technologically, but if you're out in the field and you're shooting in situ and your limit of detection is 20 ppm, you can lower what you're able to achieve by grinding and sieving and packing in an XRF cup and creating a completely fully prepared sample. And that sample, if you analyze it and can get down to a lower value, like 10 ppm, and then you send that to a lab, and you can get a corroboration with a lab of a 0.98 R squared value. So it's kind of bringing the lab to the field.
Can you explain the calibration method that you talked about earlier again?
So calibration for a specific application you're interested in, or?
Yeah, like if you were gonna go and test an area for lead-based paint, maybe like on a construction site, maybe like the wall.
So that's an excellent question. I want to know if you're trying to identify lead paint in situ on the wall or stuff that's been scraped off during demolition.
Can you explain both, maybe?
Sure. So on a wall, that's why it's so important not to switch these. Like you can't shoot with an XRF that's calibrated for lead paint on a wall down on soil and expect to get any realistic results. I keep forcing that because I get that question. Even this week I had that question. Can we just shoot chips or on the ground and identify? So what they do with lead paint is that it's a series of calibrations for each substrate. They actually identify lead paint on every single substrate and pack that all into the calibration. And so anytime you shoot painted material, regardless of whether it's on drywall, wood, ceramic, brick, it's going to give you an accurate answer because they've calibrated it to all of these substrates. For soils, you're dealing more with, you've got to have a specific calibration designed to analyze elements in soils. And what they do with that is they have an infinite thickness calibration. So the XRF is expecting to see at least 3/4 of the thickness of a sample. That's like the one thing that kind of draws its parameters. It has a thickness, infinite thickness. And a lot of the times when folks put soil into a bag, they'll put not enough thickness into it, and they'll analyze and they'll wonder why they're so far off from the lab. And that's because they don't have a thick enough sample. So even when you press on it and it pushes it down, it's got to be at least 3/4 of an inch thick. Otherwise, you're introducing error into your sample. So that's based on the way it's calibrated with the infinite thickness. And what they do is they show it pure forms of all the elements that it wants to detect, that you want to be able to identify and quantify. Does that answer your question?
Yeah, so when you're calibrating it on the gun, is that just kind of like a setting that you would put it on, or is it something?
What you're doing with the instrument, so it comes factory calibrated, and what you're performing is a calibration verification. So for soils, you'll have a soil sample with known amounts in it. You should always have and request, based on your elements of interest, a sample, a standard that comes with it. And this soil, I know that it has 31 ppm lead and 100 ppm arsenic, so that's what I'm looking for. I've got some folks that want to identify uranium, and I'm like, well, we don't have any samples with detectable amounts of uranium in it. But if you have some, so what they could do is analyze some of their soil with a lab and shoot it with the XRF. So you can take that same sample. The beauty of XRF is that it's non-destructive. So you shoot your sample, send that to the lab, you find out, okay, this is what my sample contains. That's your known standard now. It's not certified, but now you have some sort of reference point for your specific job.
Okay, thank you.
Sure. All right. Well, hey, thank you very much. If there's no more questions, I believe I'm gonna just go have breakfast.